If a cataclysm erased all scientific knowledge, one statement carrying the most information in fewest words might be the atomic hypothesis: all things are made of atoms. As the ship quivers, embarking on its voyage into the vast unknown, the adventure of a lifetime commences. The nervous crew are off on an epic journey to visit their home world's only natural satellite. Though similar in concept to the journey undertaken by the Apollo astronauts when they left Earth for the Moon, this voyage is very different. When Armstrong and Aldrin headed for history on the lunar surface, they needed only to travel a distance equal to the width of 30 Earths. Our intrepid travelers must cover a distance equal to more than 63,000 times the diameter of their home world. Compared to the crew's destination, though, the Moon is a celestial snail. It crawls around the Earth once a month at a speed of 1,000 meters per second. That may sound fast, but this satellite is whipping around at over 2 million meters per second, or just under 1% the speed of light. It's moving so quickly that it completes 6.5 quadrillion orbits each and every second. For it is no moon, and this is no solar system. Our travelers are not exploring the astronomical realm, but the atomic one. They are brave atomonauts, adrift inside the hydrogen atom. Departing from the solitary proton at its center, they are in search of the lone electron that encircles it. But their mission is a lot harder than it first appears. The electron only orbits the proton like a moon orbits a planet in the simplified Bohr model of the atom, named after the Danish physicist Niels Bohr. Modern quantum physics says that we can never know for certain where the electron actually is. We can only say where it's most likely to be. The blur of all its possible paths creates a cloud around the nucleus. Our atomonauts could therefore never land at their destination, only float into the fog of possibility. These atoms are the universe's Lego bricks. Vast galaxies swirl in the void and distant stars keep vigil over the night, but they are all built out of atoms, as we all are. Indeed, there's an entire cosmos inside you. The number of atoms in your body alone exceeds the total number of stars in the entire observable universe. Even if you started counting them at a rate of 1 billion a second, it would still take you far longer than the current age of the universe to complete the task. And as we have seen, even within those atoms themselves, there are entire complex systems to explore. And yet, at the very beginning of time, the number of atoms in the universe was precisely 0. Not a single atom in the entirety of the cosmos. So how did we end up here? Where did the very first atom come from? And just why is everything made of atoms? The Earth weighs about 6.58 billion trillion tons. The Big Bang. Except that it wasn't such a new idea to game off. The Russian physicist Alexander Friedman had already predicted the universe's expansion back in 1925, and the pair had lengthy discussions about it during Gaimov's time in Leningrad. Gaimov spent much of his early time in America working on something else, the ultimate power source of stars. Yet the focus of his attention was shifting. In 1945, Gaimov, pondering Niels Bohr's birthday, began linking his stellar mechanics to the universe's origin post-Big Bang. A debate arose: matter or electromagnetic radiation, what truly dominated the early universe? Ralph Alpher, possibly prompted by Gaimov, suggested electromagnetic radiation ruled for 50,000 years post-Big Bang. When physicists mention light, they refer to a spectrum beyond what human eyes perceive. It encompasses everything from gamma rays to radio waves, like the microwaves you use to heat food. In the young universe, light and matter coexisted, and sound waves persisted for thousands of years, so low in frequency that they were beyond human hearing. These baryon acoustic oscillations, still detectable today, kept stretching as the universe expanded. Then came recombination, a pivotal event predicted by Alpher and Gaimov. This unleashed the first light into the universe. But what exactly recombined, and how does this relate to the first atom? The weirdest object in the universe. Picture being trapped in an endless maze, every turn leading to another dead end. Light faced a similar predicament after the Big Bang, encountering countless subatomic obstacles. Initially, the universe was free from such barriers, but light quickly turned into its own captor, transforming into matter. Light, akin to energy, can shift into matter, a phenomenon occurring within a trillionth of a second post-Big Bang. This transformation brought forth fundamental particles, including electrons, necessary for forming atoms. While electrons already existed, the creation of a hydrogen atom, like the ones our atomonauts explore, demands protons. Protons, unlike electrons, consist of quarks, specifically up and down quarks. With 2 up quarks and 1 down quark, a proton carries an overall positive charge. However, these quarks, with similar positive charges, typically repel each other. How these positively charged quarks coexist within a proton remains a fascinating mystery. The solution to this puzzle lies with forces, the glue needed to stick the first atom together. Physicists know of 4 fundamental forces in the universe. 2 are familiar to us: gravity and electromagnetism. Light is an electromagnetic wave, and it is electromagnetism that repels like magnets and quarks from one another. Down in the atomic world, 2 less familiar forces are at play. The weak nuclear force governs radioactivity, but it's the strong nuclear force that really dominates here. It is 1 duodecillion times stronger than gravity. That's 10 followed by 38 zeros, significantly more zeros than there are stars in the entire observable universe. The strong nuclear force is also 100 times stronger than the electromagnetic force. So 2 quarks with the same charge may want to push away from one another, but the strong nuclear force can override this electromagnetic instinct and keep them tied together. The strong nuclear force reigns supreme over an incredibly small realm, about a trillionth of a millimeter. Initially, when quarks first emerged, their energies were too high for the strong force to bind them together. As the expanding universe cooled within the first millionth of a second, dropping to a mere 1 trillion degrees, protons and neutrons began to form. Neutrons, composed of 1 up quark and 2 down quarks, are key players in atomic nuclei. However, these particles aren't as straightforward as they might seem. Take the proton, for example. While it appears composed of 3 quarks, known as valence quarks, these make up only a tiny fraction of its mass. The rest is an enigmatic mix of gluons, particles responsible for the strong force. Gluons facilitate the bonding of valence quarks into a proton, but they exhibit their own bizarre behavior. At times, they transform into quark-antiquark pairs, called C-quarks, before recombining back into gluons. This dynamic, alongside gluons and C-quarks, constitutes 99% of a proton's mass, despite the temporary nature of C-quarks. In this quantum landscape, various quarks, ranging from top to bottom, strange to charm, appear as fleeting C-quarks, maintaining energy conservation loss. Surprisingly, experiments have even detected charm quarks at lower energies. Intriguingly, charm quarks possess almost 1.5 times the mass of an entire proton, although their rare appearance doesn't add their complete mass to the proton itself. This quantum world of minuscule particles defies common intuition, presenting an intricate and perplexing reality at the smallest scale. In the ongoing cosmic timeline, our journey toward the first atom continues as the universe cools and the speed of protons and neutrons diminishes. George Gamow emerges back into our narrative in 1948 with a pivotal letter published in Physical Review Letters. In this concise piece, he proposes a significant insight. Within minutes of the Big Bang, as the universe cooled to 1 billion degrees, the strong nuclear force facilitated the bonding of a proton to a neutron, creating a proton-neutron pair known as a deuteron. This marked a critical juncture in the universe's structural development. Stars like our Sun generate immense light by converting hydrogen into helium through nuclear fusion. Gamow, along with Ralph Alpher, deciphered the fusion process, where deuterons played a fundamental role. When a deuteron combines with a proton, it forms the nucleus of a helium-3 atom. Subsequently, 2 helium-3 nuclei fuse, creating the nucleus of a helium-4 atom and 2 additional neutrons. While these reactions currently occur only in extreme conditions within stellar cores, similar conditions were present throughout the early universe. However, this window of opportunity for fusion was exceptionally brief. It opened shortly after the Big Bang and closed roughly 20 minutes later as the universe rapidly cooled. Within this fleeting period, around a quarter of the universe's mass of hydrogen nuclei transformed into helium nuclei. Yet, the formation of the first atom required a much longer duration. Electrons, negatively charged, are attracted to the positively charged protons within atomic nuclei due to the electromagnetic force. However, this force is significantly weaker than the strong nuclear force, necessitating a drastic cooling of the universe to around 4,000 degrees for the electromagnetic force to take effect. This pivotal moment arrives after 380,000 years of expansion post-Big Bang, finally culminating in the formation of the first atom. However, the inclusion of electrons only contributes to the complexity of this newly formed structure. Electrons, discovered in the late 19th century, remain an enduring puzzle. Nearly 2,000 times lighter than protons, they're deemed point-like with no internal structure, yet their behavior defies intuition. In quantum physics, an electron's exact position and speed cannot be simultaneously known. It exists in a cloud of possibilities around the nucleus, its whereabouts uncertain. Spin, a curious property, makes electrons appear as if they rotate. Although they don't actually spin, they're spin one-half entities, requiring a 720-degree rotation to return to their starting point. This quantum dance challenges our grasp of reality, creating a maze of perplexing mysteries within atoms. The birth of the first atoms post-Big Bang released light from this quantum labyrinth. Electrons entering orbits around nuclei expanded the space between matter, allowing light to travel freely. Ralph Alpher and Robert Herman's 1948 prediction of this initial light's visibility offered compelling evidence for the Big Bang's fiery origins. Sadly, their idea lay forgotten for over a decade until seeing the Big Bang. A fresh-faced Robert Dick stands on the roof of the radiation laboratory at the Massachusetts Institute of Technology, holding a device of his own making aloft. Dick joined MIT under a cloak of secrecy in September 1941. The Second World War has been raging for 2 years, and although the United States remains neutral, it is starting to make preparations for joining the fray. They were right to. Within weeks of Dick starting at MIT, the Japanese attack Pearl Harbor, and the United States enters the war the very next day. Dick is a keen inventor with a real skill for electronics. It's in the blood. His father was a patent attorney, and Dick Jr. would go on to file over 50 patents in his lifetime, for devices from clothes dryers to lasers. At MIT, Dick focuses on radar improvements, shifting from radio waves to shorter wavelength microwaves. Curiosity about cosmic microwaves leads him to aim his new receiver skyward, a pivotal step in 20th century cosmology. He contemplates cyclical universes, envisioning a big crunch followed by a new Big Bang and the subsequent formation of atoms, coining the term recombination. Dick realizes relic radiation from this early stage should linger, visible as fireball radiation in the microwave spectrum. His plans to observe this are disrupted when radio astronomers Penzias and Wilson accidentally stumble upon the cosmic microwave background, the telltale sign of the universe's hot Big Bang origins. Their discovery, born from cleaning pigeon droppings off their antenna, wins them the Nobel Prize, leaving Dick's research unacknowledged. This cosmic microwave background serves as an indelible image of our universe's infancy. In the early universe, subtle temperature changes hinted at its future while galaxies gradually formed over millions of years. Today's map of the cosmos, spanning vast distances, bears imprints from the universe's infancy. Scientists, through endeavors like the Dark Energy Survey, have revealed the intricate layout of our modern universe. The story of atoms, from their non-existent beginnings to their abundance today, mirrors a delicate balance akin to narrowly escaping a firing squad unscathed. Imagine the universe as a massive control panel. Tweak even a fraction of its properties, and atoms, the building blocks of reality, would vanish. Forces keeping electrons orbiting nuclei, the masses of protons and neutrons, and the quarks composing them, each appears meticulously adjusted. Subtle variations in these values could erase the familiar world of chemistry and biology. Even the tiniest alterations in the forces binding particles could eradicate the diversity of elements essential for life. It's akin to a firing squad's every shot missing by chance, hinting at an orchestrated precision defying all odds. This apparent fine-tuning has led to 3 compelling explanations: chance, a deliberate act by an omnipotent force, or the concept of multiple universes with varying settings, a multiverse. And our presence in a universe suitable for atoms is akin to a journey of improbable survival, from their inception in the Big Bang to their formation within stars, planets, and, ultimately, within our contemplating minds. Thanks for watching, everyone. If you liked this video, don't forget to hit the like button below and subscribe. See you in the next video.